A very good day to whomever is watching. We are from Team Design here and proposing to you an LSS design. Moving on to overview. We will be presenting, the first and foremost is team introduction. Second is our problem statement, follow up with system summary, LLS design, power system study, and key financial metrics. Moving on to the next slide is our advisor, Ms. Basila Ismail. Moving on to the team introduction, we have myself, Afdalhan, as the team lead, and we have Akil Alkorni as the power system specialist. We have Fahan Amma as the solar system engineer, and we have Haziq Salim as the project engineer. We are required to design a large-scale solar plant which has a capacity up to 50 megawatt AC, which will be connected to the existing grid of 132 kilovolt grid.
Assalamualaikum and thank you Afdal. So I am going to present on the system overview. So as you can see in the table, it shows the PV module and we've been using Trina Solar 500 watt. It is a monocrystalline type. And for the inverter, we'll be using as requested in the Eppscom, which is SC4200 up. And the reason being because it comes with RMU and also transformer. So now moving on to next. The system performance. So before we do any LSS design or deep silence programming, we do PVC simulation to identify how much generation our LSS plant produces based on the solar panel used and inverter used. So as you can see, the table shows annually P50 and P90. P50 meaning that 50% chance our generation will be 93.42 gigawatt and 90% chance the generation will be 89.92 gigawatt. So we know the estimated range of our LSS plant generation. Now moving on to structure. So the dome structure is our solar panel orientation and we plan to do two orientations. The reason being here, as you see in the diagram, it shows a sun path diagram and there is a number 1, 2, 3, 4 until 7. So this number represent the position of sun in that range of month. And if you can see 1, 2, 3 is facing north 180 degrees, whilst 4, 5, 6, 7 is facing south 0 degrees. So that's our reason why we use two solar panel rotation. And as you can see here, this is the diagram of our panel rotation. Half will be facing north and half will be facing south. And lastly, for my part, okay, the degradation of a Trina Solar 500 watt panel. This is from the data sheet. And as you can see here, for the first 10 years, the performance will be above 90%. But after that, it will be below 90%. Meaning that for the first 10 years, it produces 90% of 500 watt. And estimated after 25 years, it will be 84.8%. But this degradation we can reduce by having constant maintenance. So that's it for my part. I will pass on to my colleague Haziq. Thank you.
Thank you Fahan Ammar for very impressive presentation. My name is Muhammad Haziq and I will focus on site layout of the LSS, the bidding price for the solar farm and also the export capacity of the plant. The picture in the slide shows the site layout of the solar power plant. The total suggested area for this plant is 90 acres that consists of main substation building, offices and the retention pond for the safety purpose of the solar power plant. The solar panel will be covered around 80 acres. To build this farm, tree cutting and land clearing must be done. So approval from Department of Environment is needed for environmental impact analysis before the work can be done. Based on the slide, our solar system design can produce an average of 9.15 gigawatt hour of energy to the grid with the capacity factor of 16.53%. The mean maximum annual allowable quantity MAAQ is 8.655 gigawatt hour, give us some advantage to expand our plant capacity in the future. From this slide, we can see the maximum capacity factor delivered by this plant is 16.57% and the minimum capacity factor is 15.97%. The decrease of the capacity factor is due to the degradation of the solar panel by 0.55% annually.
Okay, so as you can see here, this is the grid system model. This model is the same as in the PBL revision that we received for the guidance for our guideline. As we can see here, this grid system model consists of 10 buses, which is 10 nodes, or we usually call it buses, 3 generators, 40 lines, 2 transformers, 5 loads, and 1 shunt capacitor. Okay, so next is our LSS model. So this SSL inject 50 megawatt power to the grid system. And another important key we need to know is our transformers MVA sizing. So our transformers sizing is 75 MVA. So losses summary for grid system with and without LSS is total losses without LSS. Our grid suffer 1.14 megawatt, and total losses with LSS is reduced to 0.53 megawatt. Okay, next is about contingency. So we do 3 contingency, N0, N1 and N11 contingency. So what I can say here, without LSS, the line loading can be overloading if they have contingency. But when the grid system have LSS, so the LSS can help to reduce the overloading of the line. So as you can see here, I state the most important lines that we need to focus is line 2-3. So as you can see here, after I do all the line outage, line 2-3 is the most critical part. So when I do line outage contingency at line 2-3, so another parallel backup line 2-3 are having overloading up to 106% overloading. But with LSS, the overloading can be reduced to 44%. Okay, so next is voltage. So voltage profile when contingency happen. So I'll straight to the point. So if they have LSS in the system, so the voltage profile will improve. So as you can see here, I take example at voltage profile at contingency N11. So at contingency N11, I blackout bus 9. So even though blackout at bus 9, but the voltage profile at bus 9 and other buses that near generator at bus 9 all having improved voltage profile. The only buses that have no improved voltage profile is bus 1 and bus 4 because they near to generator. As you can see here, our reactive power requirements. So we started at 20% until 100, and by this graph you can see we started at 0.5 lagging to 0.95 leading, and our voltage currently still at level plus minus 10%. Okay, last is the short circuit analysis. As you can see here, we integrated LSS. The graph for the short circuit may rise a little bit, but the short circuit rating at 132 kV not exceed 31.5 kA, and short circuit rating at 33 kV are not exceed 25 kA for this simulation.
Okay, we go to the next slide. The bidding price that we set for this 50 megawatt AC project is 0.185 cent per kilowatt hour. The price has been set based on the system marginal price SMP that we analyze. This will ensure the solar power plant project remain competitive among other solar power producer. In 25 years period of purchase agreement, it will benefit our buyer over the years despite the cost of energy arise. The estimated total cost project is 3 ringgit 84 cent per watt peak, which bring up the total cost project with a price tag of 260 million. The operation and maintenance including land rental cost, is 70 ringgit per kilowatt peak per year. The levelized cost for this project over 35 years is 0.17 cent per kilowatt hour. We go to the next slide. With a small percentage of profit margin, the project itself can generate a good revenue for our investor. The estimated growth of revenue is around 7% per year. This indicates our strong financial model and financial capability in delivering this project. The return of investment for this project is estimated around 10 years period. Since 50 megawatt
Thank you for your
project use a lot of funding, 10 years payback period can be considered as the best investment for the investor.